Okay, so we're recording numbers 1, 2, 3, 4 from the 4 problem sets. So number 1, analogies exist between rotational and translational physical quantities. So translation, remember, is when we're doing linear motion, what we did in week 1. Rotational is obviously what we're doing now. Identify the rotational term analogous to each of the following. So acceleration, force, mass, translational kinetic energy, linear momentum, impulse. So basically what you're going to say for some of these problems, for acceleration, we'll call that centripetal acceleration. Let me write that more nicely. Centripetal acceleration. Mass is not really going to change. That's just still going to be called mass. So we're not going to worry about that. Linear momentum, we're going to actually call that angular. Momentum, we'll do that tomorrow. Here we'll call that rotational kinetic energy, and we'll do that tomorrow also. Force, we actually call that torque in some ways. Kind of, I don't know. In this way, it's kind of like torque. I'm not really sure about impulse. Let's come back to that. But those are some analogies between some of those quantities. Now, for number 2, explain why centripetal acceleration changes the direction of velocity in circular motion, but not its magnitude. That's because centripetal acceleration is perpendicular to velocity. So we're not going the same direction, so that's why it's not changing the magnitude, but they can change the direction. Then for 3, in circular motion, tangential acceleration can change magnitude, velocity, and its direction. That's because this right here is parallel to velocity. So it can't change direction because they're going the same direction, but it definitely can change magnitude. For 4, suppose a piece of food is on the edge of a rotating microwave oven plate. Does it experience non-zero tangential acceleration, centripetal acceleration, or both? Well, it's moving the same velocity. I mean, you'd think. Or constant velocity may actually change that. So if you look at A, B, and C, I'll do it down here. We'll make a little table. AC for centripetal acceleration, AT for tangential. So in spinning, definitely it's a non-zero. But your tangential acceleration will be 0. Oh, sorry, when it starts to spin. My bad. But then when it's at constant angular velocity, that will be 0. But this will be non-zero. Because remember, the direction's changing. And of course, when it comes to a halt, they're both 0 in this case. So that's the way we can kind of think about it. But remember, the key thing is that when you have centripetal acceleration, it's still going to be a non-zero value, even at a constant angular velocity because the direction is changing. Okay, so those are some conceptual questions. Let's keep moving. So let's look at 4.3. These are some conceptual things we'll discuss here. Okay, so here we're talking about simple machines. Here we kind of have like looks like a crowbar. Clearly here you have a pulley. Here's a ramp. I'm not sure what you call this. I mean, obviously this is an axle. I think this is a crankshaft, actually. Not 100% sure. But the whole point of machines is that it makes work easier. Machines will make work easier to do. Energy is conserved. So same amount of energy with or without the machine. Mechanical advantage is defined as that where FO stands for output force. FI stands for input force. So a lever, that's kind of what we have over here. So that's called a lever. Uses torques with pivots. And N right here, I guess is where our pivot is. And remember what torque is. Essentially your force times your radius. And typically we also multiply by sine theta, but if you're doing it at 90 degrees, don't worry about it. So this right here is your input torque. And this right here is your output torque. And remember, that's going to be your torque net, or tau, the Greek alphabet we're using, Greek letter. And you usually want that to be 0. So in this case, you could say the input minus the output have to be the same, which makes the input the same as the output, since you want the difference to be 0. So that's what's happening here. So, so if you're trying to lift something, if you use a long lever, you won't have to apply as much force. You probably won't move it as much, but you'll get more output. So force increases when the length decreases. They're kind of inversely related. And MA, just so you know, MA stands for mechanical advantage. So it's the output force or the input force. So you want the output force to be higher. So you want FO to be bigger than FI, because you want to be able to generate more force. It's also defined as Li over LL. That's because L and F are inversely related. Wheel and axle kind of follows the same thing that we're flying for a lever situation. That's kind of like a wheel and axle situation right there. Inclined plane, that's usually when you have a ramp. So less force is needed to slide up, but you obviously got to travel a longer distance, so it's a trade-off. That's why you see a lot of moving trucks. They use ramps to get stuff in and out, just easier on people. If you're using, actually, this is what's probably happening. Like, that's what they mean by a screw. But that's an inclined plane wrapped around a shaft. Some people can use a wedge. That's when you have two inclined planes. Pulleys are more popular though. They tend to have a grooved wheel. They change the direction of the force. So there's also tension that you have to worry about within the rope. That's being part of the pulley. In combination, it can decrease the force when you do a bunch of pulleys. We're not going to really kind of explore pulleys too much because that is a little bit complex when you start dealing with all the tension and stuff. So I don't think we'll really get into that. If you want to do AP physics, you will, or physics in college. But again, just the key thing here is mechanical advantage is the output force over the input force. That's kind of what I really care about. And there's a lot of ways you can actually create a situation where you have more output force and input force by using a lot of these different simple machines. If you look at one example down below, what is the mechanical advantage of the inclined plane here? So again, all you're doing output force over input force, or so obviously this guy's pulling 50 newtons, right? And his way due to gravity. Now, it's the same thing as the input length over the output length. So the input, like you're actually traveling 10 meters. And the output is you're actually lifting about 1 meter. So mechanical advantage is going to be 10. And it's unitless. Because it's a ratio. So what this tells me is that if my output force, because I'm trying to move 50 newtons, so the input force doesn't have to be that much. In fact, you only need 5 newtons to pull on it. So that's kind of the advantage there for that. Assuming that that your input force, if the thing weighs at 50 newtons, so you don't have to use as much force to pull that up. Muscles also kind of act as a simple machine. So muscles only contract and they come in pairs. So here's like your triceps muscle, biceps muscle. And obviously this person's holding a book up. Muscles are also attached to bones. close to the joints using tendons. This makes the muscle supply larger. Then is lifted. In this case, input force is actually greater than the output force. Your mechanical advantage will be less than 1. That's how muscles work. But anyway, just a little bit of terminology and stuff like that I just wanted to go over. I just want to make sure you guys understand mechanical advantage. Let's actually look at a couple problems, and then we'll do a review on waves. Let's take a look at number 7 could be a good one, I think. Let me think about that one there. Lever. Or actually, we can start with 6. So the mechanical advantage of a nail puller, similar to the one shown in figure 1. Okay, so I guess that's what's in is pulling a nail. Where you exert force of 45 centimeters from the pivot, and the nail is 1.8 centimeters on the other side. And what minimum force must you exert to apply a force of 12 newtons to the nail? So you definitely need to pull the nail. It's in there really good. So remember, mechanical advantage is going to be your output force divided by input force, or it could be equal to the input length over the output length. Now in this case, the output length is 45 centimeters. So that's how long, I guess, this nail puller is. So, and you don't have to change units if these units are the same. And that's only going to move at 1.8 centimeters. So the mechanical advantage, if I work that out, will be 25. So this means that 25 equals the output force. Remember, the input force was, actually no, the output force is 1250. So the input force, and you get 50. So that's the problem I could probably put on our test, something like that. And you know, you kind of see other problems are kind of similar in that regard. But the math is pretty simple. I don't want to do any of the more complicated ones. So we'll just leave it at that. Okay, so that's 4-3. All right, so next up, what I want to do is I want to go over the review for waves. Before that, let's see if there are any questions about circuits on 6.5 through 70. So let me share my screen again. So, were there any questions that anyone had about 6.5 to 70 that they probably looked at last night and were confused? I'm going to go over all of it anyway, but anything that's kind of pressing that you wanted to share or discuss? Okay, so let me set the, actually we are still recording, so that's good. Okay, so keep the recording going. So for 65, if the current at a given point is 2.5 amps, how many electrons pass that point in the circuit in a time period of 1 minute? Okay, so this is one thing I didn't quite go with you guys. But remember, 1 ampere, I won't ask this on our test, just, you know, but 1 ampere is 1 coulomb per second. 1 coulomb, if I'm not mistaken, covers about 1.6 times 10 to the 19th electrons, but you can always just look it up in case you're not sure. So the beauty about, you know, these cell phones. So let's see here. 1 coulomb. Actually, as close as it's actually 10 to the negative. So that's a single electron has that charge. So actually, I'm a little off there. So I have the other way around. Yeah, 1 electron equals 1.6. An electron is very, very tiny, negative 19 coulombs. So 1 coulomb, actually, if you were to invert it, is 6.24 times 10 to the 18th electrons. So we have 2.5 amps. That's 2.5 coulombs per second, and it's for 1 minute. Remember, we have 6 seconds in a minute. That's easy. And 1 coulomb is 6.24 times 10 to the 18th electron. So coulomb is representative charge, and then you would just multiply that out. So a lot of electrons are passing in 1 minute. In fact, if you're curious, 6.24 E18 times 60 times 2.5. So it winds up becoming 9.36 times 10 to the 20th electrons. So a lot of electrons passing through in that short period of time. What is the resistance of a typical 40-watt light bulb plugged to 120 volts outlet in your home? Now remember, power equals IV, and V equals IR. So if you want to get resistance, you can actually substitute, where I equals V over R. So power equals V over R times V. Remember, your power is 40, 120 squared. And solve for R. So something like that I could also ask on our test too, something just very straightforward. You've worked out, it'll be 360 ohms. Remember, that's similar for ohms. So that's 6566. Again, the answers, I have given you guys a link for that. So any questions about 6566 so far? Nope. And again, if you go to Schoology and click on this and click on that, and you can see they have all the worked out solutions there for all that stuff. So let's keep moving. Let's look at 67 and 68, 69, 70, and then I'm gonna have you guys do some practice on waves after that. Okay, so for 67, determine the length of a nichrome wire. The resistivity is given to you right there. Required to produce a 1 milliamp current if a voltage of 1.5 volts is impressed across it. Diameter of the wire is that. And again, you're trying to get the the length. So remember, there's a formula that goes with that. So it looks like this. It's like a P. Resistivity is defined as, and actually, probably should look that up. So I think you're divided by area, if I'm not mistaken, but yeah, R equals P. So I had it the other way around. So let me redo that. So that should make sense because L is just length of the wire, A is a cross-sectional area. So we know the resistivity is 150 times 10 to negative 8 ohms times meters. Length is what we're trying to solve for, so times L. The area is 1/16 of an inch, but we do need to keep it in terms of meters. So 1/16 of an inch will be 1/16 times 2.54 centimeters. We want to convert that to meters. Just going to divide by 100. 0.0015875. But remember, it's a wire, so it's got a cross-sectional area. That's a circle. So you square it and times pi. So your cross-section area is going to be 7.917.
Mr. Almashni,
Oh, yeah, go ahead.
is it pi r squared for the bottom part?
Yeah, for the area, yes, it will be.
Okay. So
yeah.
would it be half of the 0.0015?
Oh, because it's a diameter. You're right. Yes. Yes. So let me backtrack just a tad. Yes, we do need to take half of that. So it's a 0.0015875 divided by 2. So yes, I do need to do that. So 0.0015875 divided by 2, then square that, then multiply by pi. Yes, thank you for correcting me on that. So area is actually going to be 1.979 times 10 to the -6 meters squared. So that's what I'm going to put down below here. And so we see that these units will cancel, and liters and length is going to be meters anyway, so that's also going to cancel. So you're going to be stuck with ohms. Now the resistance, you told 1.5 volts, 1 milliamps. Now remember, V equals IR. So 1.5 volts. Your current's 1 milliamps, so it's going to be 0.001 amps times your resistance. So your resistance is 1,500 ohms. And then you can solve for length. If you do it all correctly, times 1.979. Yeah, so length is going to be about seems a bit long. I have to double check the answer here, but this seems like to be a really long wire, so let's check out the answer key. No, that's about right. Okay, so it's about 2,000 meters. So, okay. So Soviet. 68 is dealing with power and energy usage. So let's do a little review there on that. So hair dryer, coffee percolator, that's like the old school coffee maker you see like in motels now these days. Everyone's got now the fancy machines. Light bulb, again, we tend to use LEDs these days. An attic fan, actually that's kind of a good thing to have if you do have that. Microwave oven, most people have that. And the hours per day that those are in use. So we do want to get the power and then energy consumed, and then the cost. So remember, and then this is also 120 volts. So remember, P equals IV, and your voltage right now is 120. So you're just doing, 120 times 12. So is that many watts? Actually, I'm going to convert these to kilowatts, just so you know. That might make things a little easier. So 1.44 kilowatts. This will be 1.08 kilowatts. 100 times 12 is actually 12 kilowatts. It's 12,000 watts. 140 times 12 will be, or times 120 will be 16.8 kilowatts. And 8.3 times 120, 0.996 kilowatts. Now, energy consumed, sorry, the kids are a little noisy. So, energy consumed. Now remember, kilowatt hours considered to be energy, because remember, a kilowatt is 1,000 watts. Remember, watt is a joule per second. So there's already units, kind of time units built into it. And to get a kilowatt hour, just simply multiply kilowatts by the hours. That's all you're doing. So this will be 0.144 kWh. This will be 0.108 kilowatt H. You're leaving the light bulb on for a while, so there'll be 96 kilowatt H. Attic fan, there'll be 168 kilowatt H. Then the microwave's not much. That'll be 0.249. Then you want the cost, and it's 13 cents. So you multiply each by 13 cents. So that's going to be, and we're going to do daily cost just for now, just so you know. We're doing a daily cost. So that's 0.018. So it's not much to run the hairdryer. And you're doing for 0.1 hours is like for about 6 minutes. Not costing much money. If you multiply that by 0.13, costs that much sense. 96 times 0.13, that will cost a bit more. So so 100 watts is pretty bright. So and you leave it on for 8 hours. That's quite a long time. So you have that. An attic fan. So let's see here. That's 140. Oh shoot. Yikes. Okay, I made a huge mistake here. We already know the watts. That's dumb. So we need to update this. I thought that was current. That's a lot of current. My bad. So that's actually just 0.1 kilowatts and 0.14, because that just seemed really expensive. Like, oh, geez, my energy bill is going to be crazy. But times 8, so it's 0.8 kilowatt hours in 10 hours, so that's 1.4 kilowatt hours. Then if you multiply by the cost, 0.13, so you have that, and the cost here, 1.4 times 0.13, 0.182. And then lastly, if you have 0.249 times 0.13, it's 0.032. So that's just going to be your daily cost. So if I add all that up, so it comes with about 35 cents. And then times 30. So my energy bill will be about $10.50. We're doing all this stuff here. Of course, you might have other stuff going on, like you have an oven, you have a refrigerator running, maybe have an electric water heater, maybe an air conditioner, or electric central heating. I mean, so a lot of different ways that can all add up. If we look at just that answer key, yeah, about $10.50. So yeah, I mean, I could have something like that too in our test. And then let's keep moving here. So 697. I'm gonna have you guys around 1 o'clock. I'll have you guys do some work on waves. So if the copper wire used to carry telegraph signals has resistance 10 ohms for every mile of wire, what was the diameter of the wire? Okay, you know copper, that's Cu, and that's 1.7 times 10 to the negative 8th ohm times meters. So remember the formula is this. Okay, let's see here. So resistivity is 10 ohms. Resistivity is this. Your length is 1 mile. So 1 mile, you already have the, so 1609 meters. And we want the area. So you solve for the area. Move things around, it should be 7, 10. 10 to the negative 6, and that's meters squared. So remember, area is pi r squared. So divide that by pi. And then square roots. So radius becomes really small. So diameter, you got to multiply by 2. Which actually will be 1.87 millimeters. So a really tiny wire. Again, you can always check your answer keys for all that stuff. What did I do wrong here? Yeah, I got the right area. Think about this. Square centimeters, if I kept it that. Not quite sure what I may have done wrong. Yeah, because we want to divide by pi. Yeah, not quite sure what I did wrong, but we'll just move on. Lastly, number 70. Determine the resistance of a 1500 watt electric grill connected to, well, that's pretty easy. Remember, power was V squared over R, 1500. Just work it out. So you should get about 9.6 ohms. Which we have right there. So, okay, perfect timing. So now we're ready to have you guys do some review on waves. So you want to get that packet out. So packet looks like this. Let me clear. I'll stop the recording.